So we spent some time talking about wires and how things are connected physically. Let's move up a level and talk about how they're organized, or look at it from more of a software level. You can't have a network just of a bunch of clients connected to other clients connected to servers, and they're all just sort of transmitting. Needs to be some control for that transmitting. And so there's a couple different models that we have. One is called the client server model, and that's where you have a central computer called a server that's acting as a resource, and this stores files, maybe does some computing, acts as a gateway to the internet, does security for these clients, making sure only the right people log in. In this model, normally the clients don't really talk to each other. They're always communicating with the server. And the client server model is something certainly very well known in the business environment, but your home network is still a client server model. That router or cable modem combination is a small computer. It actually is a server. It runs Linux, and it is the server, and all the things that you connect into it are clients of that server. Now there's a less common network model called peer-to-peer, and that would be where there's no server and each client is connected to each client, and they, you have to do a lot of setup and configuration. Sharing is peer-to-peer. Links need to be set up manually. I suppose there might be one client might serve as perhaps a gateway, but then you're sort of back into this slight variation on a client-server model. Now, beyond the client-server model, I guess there's another word we use for a more complicated client-server model. It's called a domain-based network. It's much more controlled, much more secure. In that we use the word domain in that computers that are connected, the clients that are connected, belong to a domain, and there is a domain controller, one of these servers here, that controls whether or not you can actually log into the computer. When you log in, when you have a domain-based network, you're not just logging into this, you're really logging into the domain server. Security policies are much more prevalent and tighter. The domain controller assigns names to clients as they're plugged in. PCC network is very much a domain-based network, and that central telecom room has all these servers for the PCC site, domain controllers, other networking functions, going out to well, I'm sure it's actually bigger than just a T1 line. It's a fiber line out to the world. Now, let's talk about, we've established this couple network models. What makes these network models work are network protocols. And the protocols are what assemble packets into meaningful things. So we have all these packets, MTU maximum data in each packet is around 1500 bytes. A file transfer, video stream, web page request, graphics, all needs to be is made up of a packet. So we need to have a protocol for breaking complicated data down into packets. We also need more meaningful computer names and addresses beyond just that physical single MAC address. Now, protocols work at the operating system level, and the name of that protocol that we're using is called TCP/IP. It's usually pronounced just TCP/IP without the slash, and it stands for Transmission Control Protocol Internet Protocol, and it defines how data is formatted, addressed, transmitted, and received between computers. Now, the TCP/IP, actually the whole networking system, theoretical foundation is this idea of layers. To get from one system to another, your data goes through several layers, and we've been talking about the physical layer quite a bit with the cables and everything. That's at the network access layer. Interface card, NIC, network access layer. It's all called the network access. You go up to data link layer. We didn't spend too much time on that, but that's still down at that network interface card level. Then we move out of the network interface card into more the software level, and we have an internet layer, transport layer, and then when they say application layer, that is things like applications. I mean, web browsers, voice over IP telephones. That's an application layer. And if you go on to take Datacom, they'll spend off and on most of the term actually just dissecting and discussing these layers. After you come out of Datacom, you have this memorized. So here's a kind of restatement at that link layer. That's the Ethernet we were talking about. The internet layer, IP, the single big concept there is that every connected device has an address, and that is interpreted at the internet layer. The TCP layer defines how data is exchanged between units, how files are broken down, how data gets from your smartphone, your laptop, how data gets from there to, say, a server halfway across the world. The TCP layer, which is quite complicated, handles that side of things. And then like I said, we have the application layer. HTTP is part of the application layer. It controls how web pages work, how you ask for data, and how data is sent back to you to create a web page. So at that next level, that next internet layer, the IP layer, we're going to introduce a new level of addressing called an IP address. Now, we had this idea of MAC addresses, and MAC addresses, once a manufacturer makes a device, they get a special number assigned from a database. Until you throw that device away 5 years from now, 10 years from now, 1 year from now, it's always going to have the same MAC ID. These are kind of not easy to use. There's no relationship between this MAC ID and this MAC ID. This might come from one manufacturer. This one might be from another manufacturer, would have a different number. Suppose this computer here wanted to send something through the internet, a web request. How does this computer have any concept of what this computer in Texas's number is? So they came up with another level of addressing where the addresses are assigned and they're going to follow a certain format we're going to discuss in a second. But I know it's more numbers, but it's more organized. And so you see these two machines here, they start with the same number, 192.168.1, differ by one digit. And over here we have this PC, and this could change, but it has the IP address of 4534699. So if this computer here wants to send a web request, it knows it has to send it to this IP address. And it'll make its way through the switch. The switch will know what to do. The internet will know what to do with, kind of like a phone number. Okay, 45, that belongs in this state. 34, that belongs in this city, or however they've divided it up. This server could be replaced with a different PC and different MAC ID. Wouldn't make any difference. The IP address stays the same. The switch, in a sense, has the first three sets of numbers. Everything on that connects to that switch, and in this case we have it set up there could be 255 different computers, but the next PC would have the next new address 192.168.1.102. So an IPv4, it stands for Internet Protocol version 4 address, has this dotted decimal notation. So this is an address, a decimal dot decimal dot decimal, and each of these fields, there's no hex here, each of these fields is a binary, it's a byte that can have a value from 0 to 255, and there's 4 numbers in there. Now a long time ago, well, it still is, there used to be address classes. PCC would have a certain starting number, your house would have a different starting number, a government would have a different starting number. Now there's a little bit more flexibility. You can't draw conclusions from that. The one thing you can say is that generally the first 3 digits are the address of a network or a building or a room, and the last byte is the address of a computer, like inside that room or inside that company. Now, this doesn't allow for very many numbers. It's only 32 bits total, 2 to the 32, which means that if every computer in the world, every computer, every smartphone, every embedded device that's wireless has an address, you're limited to about 4 billion different devices. And believe it or not, that's not enough. Oops. So IPv4 is running out of addresses. They came up with, actually a long time ago, something called IPv6, Internet Protocol version 6, and they're giving it 128 bits of address instead of 255. Almost all devices these days are IPv6 capable, but depending on how your network's set up, they still may be using IPv4. And actually when you look at stuff, most things are still IPv4, like on a global or national level. Now let's talk about a specific detail that can be confusing about IP addresses. That's something called the subnet mask. So, if I have an address of 192.168.4.2, that's the full address of a computer. But that has 2 parts. One is the address of the network, which I'm going to define as these 3 binary bytes here. And then the address, the 2, that's the address of the computer on the local area network. So I've got a building, and inside that building are possibly 256 different computers. The address of the building is 192.168.4.2, and the address of a computer inside the building, I have computer 1, computer 2, computer 3. All right. Now the way networking software works is it needs a subnet mask to separate out the network address from the computer address. And here is our IP address. Here's the binary equivalent. Here's the subnet mask, binary equivalent. And these 2 numbers are ANDed together. That masks out or strips off the device ID. And so this, just leaving the networking software with, this is the address of the network, 192.168.4. By a similar process, the device ID, the host computer address inside the local area network, can be derived by doing something similar, and we get the 2. So address of the local area network, address of the PC in that network. Most of the time, this is the value of the subnet mask if you ever have to fill it out. However, sometimes this allows 256 or 255 different computers on the network. You might see a subnet mask of 255, 255, 127, which means this bit here is a 0, and that would imply that there are double or 512 computers on this network. Comcast, I think, uses if you were to ever get at their level in the neighborhood, like that serves an apartment building or several streets or something, their subnet mask is usually 255, 255, 255, sometimes 32, 30, 31, or 63. All right. Now, there's some details about an IP address. There are some special addresses. 127.0.0.1 that's always interpreted by the computer as a loopback. Loopback meaning you could have a computer not connected to anything, no network, and if we're running a web server on that computer, because it's not connected to anything, couldn't see it surf the web, but it could see its own web server, and by using this address. So networking software reserves this address for itself. Every computer has this address. There's a bunch of multicast and test addresses. Multicast means a networking device can send a single Ethernet frame to a switch or a router, and if it's sent to a multicast address, that packet will be forwarded to all the computers, whether they ask for it or not. Now, what's made the system work so far is this idea of network translation or a private address. I'm going to switch to this little diagram I found to explain this. So, the world, the internet, whatever, is made up of this kind of structure. If you remember, we saw a long time ago in the previous video about a firewall, a brick wall separating, client computers from the world. The modem router combination is our firewall, and every one of these modem router has a unique IP address. So in this picture, this one's 84.102.272.112. If I'm connected to the internet, I can guarantee there is no other house, apartment, modem in the world that shares this address. This is what I call globally unique. Every one of these devices assigned by your internet service provider, assigned by the internet, has a distinct number. Okay. This is the public address. Now, behind that router, we have private addresses. And what that means is if I have this set up here, my PC that I'm typing on or accessing internet might have the address 192.168.0.2. That's assigned by the router. You plug your computer in, the router gives that address. If you look at the information, that seems like that's the address of the PC, and it is. What happens is that this is private, and if I say go next door to my neighbor, they might have a public address of 84.102.272.113, but inside the house they're going to have this same list of addresses. And so that's how we've managed to exceed that 4 billion device limit, because the internet is full of these firewalls with these modems and routers, and behind them are local computers. Now, PCC, for instance, probably has, instead of 255 like we were looking at before with the subnet mask, PCC probably has room for 10,000 computers behind its firewall modem router device, which is quite a bit bigger than this. If I go down to PSU is going to have a different public IP, but they're going to have that same block of possible 10,000 addresses. Now, what happens in address translation is if I'm on this PC, I make a request to some server up on the internet. It goes in here. The router sends out my request as if it belongs to me, as if I'm the computer and this is my address. The server gets the request, comes back, sends a web page back, and the router remembers who is asking for that web page and forwards all that web page data back to the right PC. So the address is translated from here, translated to this address. I like to think of it as kind of like the globally distinct address is like the front door of a high-rise apartment building. The front door has a unique address, street address, and number, but each apartment just has the generic 1, 2, apartment 1, apartment 2, apartment 3, shared by the apartment building across the street. Again, private addresses are not globally unique by themselves, but when you combine them with the public address, your computer has a unique address. And so on Comcast systems it can change, but on a lot of systems, if you go to anybody's house and look at their network is going to have the address 192.168.1.0 for the gateway, and then all their IP addresses are just going to start with 192.168.1.2.3.4. Now let me look at I've typed something called ipconfig. This is my command window for my PC. And I want to focus in on a couple things here. So my network adapter does support IPv6, and it's assigned a default address, and this is what an IPv6 address looks like. It's a lot longer. Again, this is 128 bits. The IPv4 address, this is the address that my router that's connected to my cable modem assigns me. So on Comcast systems, it usually starts with a 10. So the address of my network, private address of my network is 10.0.0, and the PC on that particular network is 158. That's why my subnet mask is 255.255.255. If I want to send information, a web request from this computer, the networking software sends it to my gateway, which is 10.0.0.1. Normally on a system, your gateway is always the address of your network with just at 1. Now if I go, I'm just going to type in here, this isn't actually Linux command, but if I go look at my router menu, I can see that my WAN, my globally unique address, actually at the moment is 24.22.118.2.238. Oops, the 8 in there. So my router has this address, and so this number here is totally globally unique. Only one exists, or only this is the only address that exists in the world, or with this number. My neighbor probably has 24.22.118.239 maybe. Okay, let's get rid of that. Now, there's a second level of addressing that we can think of, and these are ports. So TCP/IP has this notion of ports on each PC. So in addition to its address, a PC also has a possibility of basically 64K different ports. And the way we would think of ports as, and I know I'm going away from that, similar to that apartment building analogy, think of your house address as an IP address. So if I take my house, which doesn't have apartments, has a front door, street address, that's my IP address. My ports are different ways to get into my house. And if I get a visitor, I want them to go to the front door. Package deliveries to the back door, cars to the garage door, mail to the mail slot, things like that. And this helps computers deliver the right packets to the right place. So if I was running a web server on my computer, that web server software, which is using the HTTP protocol, has a service watching for incoming traffic being sent to port 80. I might have an email server watching for traffic sent to port 57. And with Microsoft, there's a countless number of other ports that are used for different reasons. If you're running VNC, you might have a VNC server that's looking for VNC traffic at port 5901. Now, so far we've talked about IP addresses. So we've left MAC addresses long behind. Then we talked about how every computer on the network, on the internet, gets assigned an internet protocol address. They're still numbers. They're still hard to remember. That's why they invented text-based web addresses. And what supports text addresses is something called the domain name system. And that's like a giant phone directory that keeps track of names and then IP addresses. Now, there used to be 13, I think hierarchically, legally, there still is 13 root name servers, like top-level phone directories, and those always had the latest information. Frankly, now, it was that way for a long time. That wasn't very reliable, so now there's actually lots of alternates and subroot name servers. Everybody's keeping track of who's who. So for instance, if I have a web server running in Oregon, www.pcc.edu, that goes to a specific address. That information is actually stored in the root name server, probably in China. And information gets there when you buy a domain and you register a domain name, you register a name. At the time you register it, you also have to give an IP address. And so your computer doesn't need to keep track of all these addresses or IP addresses. It just has to know the IP address of the name server. Let's see. So my DNS server through Comcast has the IP address of 757557575. That maps to a name system, but all my PC has to remember is this address here, and that gets set when I ask for an IP address. But when I pass the web address cnn.com, I'll get back the number, the IP address that cnn.com is using, and my browser doesn't send a web page request to cnn.com. It sends it to 157.166.255.19. And at this IP address is probably not a single computer, it's actually probably multiple. It's the gateway, and your web request probably gets passed to goodness knows what address. Now, let's talk a little bit more about domain names and web addresses. So the HTTP is a way of, it's inserted into the packet, tells it's a web page request. FTP is for file transfer protocol. There's other headers for email. HTTPS is for secure web pages. So anytime you form up a packet to be sent across the internet, you have to tell it which service to use, which also actually then ties it to a specific port on the other end. Now, names can have subdomains. www.example.com, that routes to the server handling web pages. There's also a server called mail.example.com, and that sends traffic to the server handling mail. You can have actually up to 127 level of dots, although I've rarely seen more than one or two. This .com over here, that's called a TLD or top level domain. There is no com server, no edu server. There always has to be a name in front of it. It's called a root zone, and there used to be a lot of .coms, .govs, .orgs. It was a fairly limited number. There still is .com, .gov, but they've opened it up, so now there's I don't know, I haven't kept track of how many different TLDs possibilities there are, in addition to the country names. The United States is the only country on the internet that doesn't require a .us. Everybody else is .uk for United Kingdom, .jp for Japan, and so forth. Now, so we talked about IP addresses, but we didn't really spend time on how those IP address numbers get determined or delivered. So again, that's done with something called a DHCP, Dynamic Host Configuration Protocol. Again, the MAC address is fixed to the device. Normally you can't change it. So you have to assign the IP address. Now, on each machine, you can do what's called a static IP address. That means that you, the computer operator, assign a unique IP address to each and every machine on the network. You can't have any conflicts, and it better not change. Otherwise, you will have conflicts. And a conflict is where you have two machines with the same IP address, and the router and the networking hardware won't know where to deliver things. That's static, and in a corporate environment, many resources are statically assigned, and in some smaller office and home networks, things are statically assigned. So at my house, all of my wireless access points are statically assigned. I give them an IP address. I know where they are. They don't change. And when Comcast assigns my router an address, that's actually, I know there's a computer doing it. It's not a person doing it. It's a computer doing it, but it's static to me. Besides static, there's this thing called a dynamic IP address, and that relies on a DHCP server that keeps a table of IP addresses and assigns those IP addresses. So when you connect a computer to a network, plug it in or connect via Wi-Fi, your computer sends a broadcast packet to port 67, and that goes to every port 67 across most of your entire local area network. Now, most computers don't have port 67 open. Only the DHCP server is watching for port 67 traffic, so it gets ignored by everybody else. All right, the DHCP server gets your request. Your request is saying, "Hey, give me an IP address." DHCP server responds with a lease offer. Your computer accepts the lease offer and sets the IP address, what is given by the DHCP server, gets some other information about which gateway it should use, and then that lease is guaranteed for a length of time, depends on the system, sometimes 3 days. When that starts to expire, the computer will ask again for that IP address. And here I brought back my command window, which I figured out how to make bigger. This time I use the IP config/all command, and I have a lot of stuff on my thing, but my main wired Ethernet connection is Ethernet adapter local area connection 5. That's the networking chip that's on my motherboard. This is the MAC ID of that device. DHCP enabled, again, that IPv6, although I'm not actually using it. IPv4 preferred means that if I power this computer off and I have it off for a week and I plug it back in, the DHCP server will say, "Oh, you want 10.0.158, no one else is using it, I'll give it to you." Subnet mask. So this one's actually getting a long, a week, a long lease, a week and a half or so. Whenever I rebooted this machine or something, say back on Friday, May 19th, it's there. Tomorrow, sometime in the morning, it's going to ask for a new lease again. It should happen automatically. Again, my gateway is 10.0.1. Any internet traffic I send out goes to this place first. And that, coincidentally, for most setups, that's also the IP address of the DHCP server, the one that gives out IP addresses. Some other things about why DHCP is important. Most broadband internet providers do DHCP. For consumers, it's always DHCP. It's always dynamic. What that means is you may turn on your cable modem in a week and you might have a different IP address. That's okay, because you don't really care, because no one's trying to reach your computer. You're always going out. Now, in practice, it rarely changes, but there's no guarantee, so you can't register a domain with that particular IP address, because it might change. Businesses and people that need it can pay for a static IP. That means from your broadband provider, they'll tell you what address they're giving you, like over the phone or in an email or letter or something, and you'll program your router with that address. DHCP in your home business, typically you don't care what your router gives you, but again, like I said, you may want fixed IP addresses for printers or other servers. Here I brought up my routers management page, and my system is designed to, this is my gateway 10.0.0.1, my subnet mask. I could change these, but normally I wouldn't. But my DHCP server, I left my domain name blank, but my DHCP server hands out addresses from 2 to 199, and everything above 199 is normally fixed, except for the 50, where I used to have an old printer that was assigned to 50, so it won't actually assign things to 50. It's statically assigned. I have some other devices that are statically assigned. They're not on this list. Like for instance 10.0, I type this into the browser, it takes me to the management page for my one of my wireless access points, which has a MAC address on the LAN side. Well, we're not interested in that. Anyway, that's a statically assigned address. So let's talk about some other types of networking hardware. So I've been throwing out this word, a router, and a router receives and forwards data packets for multiple devices. And a router can range from the little thing that might be somewhere in your closet or your desk or whatever, to a backbone router for the internet. And these are big, refrigerator size type machines. Routers have tables and tools for doing the network address translation that we talked about. There's other devices called a switch. Now a router actually incorporates the functionality of a switch. A switch just learns the MAC addresses of attached devices and only forwards packets destined for those MAC addresses. And sometimes you'll see the word SOHO. It just stands for small home office, although in practice there's not much difference between a consumer product and a SOHO office product. There used to be, and you may still find them, I suppose, in some installations, something called a bridge. A bridge is also called a repeater or a hub, and it just repeats all packets to all ports, whereas a switch only sends things where it's meant to go. Now this is actually my old router, but it's simpler. So my router control panel, set to automatically configure or obtain IP address from the provider. My external IP address at the time I made the slides, which was 2 years ago, at that time it was 67171.161. Now it starts with, I think, a 2.3 or something. My subnet mask, this is the Comcast assigned subnet mask. That meant my network address is this, and the host computer had this address. I had a gateway that was a Comcast provided. This is where the router, when it wants to, the router serving as a gateway for my local machines, but the router has a gateway it talks to as well. When it wants to send traffic out from your PC, it forwards it onto this gateway, not up here, down here, 67.171.60.1. And I had 2 lookup hosts. The reason there's 2 is in case there's a problem reaching this one, the system will, not get a response and then go and ask for something from this one. Other kinds of common network devices, basically I'm just throwing a lot of names at you, but we have wired adapters, and the adapter or network interface card could be PCI, could be PCI Express, could be USB. Sometimes you can actually, if it's on the motherboard, you really don't care what interface it's using, although it's using a form of PCIe. Wireless adapters, Wi-Fi. Again, any number of connections, often USB or PCI Express. Switches we talked about. Gateway firewall. So the gateway firewall, well, the gateway is the piece of networking hardware that takes things from our main network and forwards them out to the internet. The firewall is something that prevents unwanted packets, Ethernet packets, coming from the internet and hitting into our network. So we only want to see, coming from the internet, things that we ask for. The system wants to ignore everything that's not asked for. Otherwise, your network would be flooded with traffic and your machines would be unprotected. We have some other things. So wireless access point is something that just provides Wi-Fi services. It's just an access point for devices to connect their Wi-Fi into, and otherwise it's connected to the wired network. Now, this is just to kind of give you more picture of, this is my old router, but it's the LAN, local area network. It's all the machines that are on my system. This was the MAC address of the router, IP address of the router, again that same subnet mask. And I had, at the time I had clients, I don't remember what client that was, but this is my voice over IP box, my laptop, my PC, and my wife's PC. I had 5 active clients, a list of their IP addresses that were granted, and this is a list of the MAC associated MAC ID addresses. And sometimes this is, the operating system may or may not supply the name here, so there's something called hostname star. I don't know what that is. I guess I looked up on this one, I looked up the MAC address of Sapur. I didn't know what that meant. This is the MAC address. If I click on that on my router, it brings up a window and it says, oh, that was a product made by Cisco. It doesn't actually tell you what the product is, but gives you a clue about maybe what it is on your network. Now there's some Windows IP tools that we have, and these similar things exist on Linux as well. Ping sends a packet to the IP address or web address, tells you if the other computer is alive or disconnected. Not everybody responds to a ping, but if I ping, okay, so I just sent a "Are you alive?" to google.com. That's the name. The DNS server returned me this IP address, so I sent the ping to that, and I got 3 replies, sent 32 bytes, took 27 milliseconds. This one took 27, this one took 30, this one took 26. TTL is time to live. This is like the quickest way. If you have something hooked up and you know it should be there, and you know the IP address, if you ping it, like so if on my local area network, if I ping 110.0.0.1, this is sending to my router. It's a very fast connection in my home, less than 1 millisecond. It's not going halfway across the world. But if I ping 110.0.0. I think there's nothing at 55. It'll sit there and say, finally come back, destination host not unreachable, means that system's not alive. Trace route, I don't know that it's that useful, but if I do this to google.com, not all routers report who they are and what they are, but let me get this down here. It's kind of trying to figure out how many places that packet's going. So I'm going to send a request to Google. First goes to my router. This is some device in Comcast probably. Goes through a Beaverton Comcast device, another Beaverton Comcast. Let's get that back up there. Oh, that's what I get for resizing. Let's do that again. Tells me that it took 8 milliseconds to get to that local device. And so let's see, we're going through a bunch of Comcast addresses down to the Bay Area. Backbone, iBone probably means backbone. Here we probably made it out of the Comcast network, and now we're into some other network, possibly a Google network. We will get there eventually. And so you can see that it took a long time, actually, well, not a long time for us, but a long time for computers, and several hops. Had to go through several network routers and switches to get where it needed to go. IP config, we also looked at that. So IP config, there's on Linux, config, it's IF config. On Windows, it's IP config. Just tells me if I have an address. Sometimes if you see an address 169 something, That's another one of those trick addresses. So if you do this and you get back 169, anything starting with 169, it means you're actually not connected to anything at all. 169 is another one of those special addresses that is used to actually tell it's the network adapter telling the operating system, I'm not connected, but I'll give you an address anyway. It just doesn't go anywhere. So just remember, anytime you hook something up and you see a 169, it means that there was no either it's not hooked up, or maybe something is not working downstream. The DHCP server is not granting addresses. We still have NS lookup, so if I do NS lookup, just tells me what the IPv6 address is and the IPv4 address of google.com. It's not authoritative because Google actually has a lot of IP addresses, but if I could let's see, what if I type ns lookup pcc.edu 209.152.146.213. Now, for configuring internet stuff, most NICs are on the motherboard, not cards. Some PCs will come with multiple, for extra bandwidth, they'll come with extra network cards, multiple Ethernet ports, sometimes on the motherboard, sometimes it's something you install. It's almost all, installation is pretty automatic these days. If you get a situation where you have not connected, may not be clear. Again, if you see that 169.254 address, it means you have an IP address, but it doesn't go anywhere. Okay, here I'm going to show you some things you don't normally have to modify, but I brought my settings up. I'm going to click on that. These are software adapters for VPNs, but this is the one I'm using. I'll right click on that, go to properties. A lot of things are up here, client for network. I'm really just interested in the Internet Protocol version 4. I'm going to go up properties. I'm not going to change anything, but I'm using DHCP, so it's obtaining it automatically. But if I wanted to statically assign something, I would click this, fill in the IP address that I came up with. Again, that subnet mask, which is usually 255.255.255.0, and I'd have to give it the gateway. And then here, DNS, it's automatically happening. I'd have to fill in the DNS addresses. And there's no lack of advanced options that you can get carried away with here. All right, let's get rid of that.